In 2024, a large streaky fireball appeared over Southern California. It was witnessed by tons of people who are obviously curious about what the heck they just saw. Was it a large meteor, a failed rocket launch, a dying satellite? Well, in a way, tracking down the answer came not from looking around, but from putting an ear to the ground and listening. Our ability to track things like this, to figure out exactly where they came from and what they are, isn't quite as good as you might think. We all see the dash cam and doorbell videos that get posted everywhere afterward, but the information you can get from those is limited. Telescopes can give you much better data, but that's still only if they can see the object, so only while it's burning up brightly, and assuming the clouds cooperate. And you're probably thinking, what about radar? But that actually has trouble tracking objects that break up into fragments, or objects that are in the process of burning up. So surprisingly, one good option to help here is to use seismometers. That's something seismologist Ben Fernando demonstrated when he worked out where that California fireball had come from.
Seismic sensors are very good at detecting sonic booms. So sonic booms are basically the shock wave that objects produce when they enter the atmosphere and they're going faster than the speed of sound. And the big advantage of working with sonic booms rather than radar or optical is that any time an object is going supersonic, it will produce a sonic boom. And that sonic boom will, in general, at least partly propagate down to the ground. And in general, each station, so each point on the ground, will only record that sonic boom once.
Seismometers measure ground shaking, which gets produced when booms traveling through the air reach the surface and convert into shaking energy in the ground. Now, if you're wondering how a seismometer knows the difference between that and an earthquake, it's because seismic waves don't create the same shape on a seismogram, and because they travel through the ground way more slowly than these objects streak through the sky.
There's first of all the information you can get from a single station. So we tend to call them N waves, and that's because you have a wave that's basically flat, it goes straight up, which is the first bang, slow back down to a low, and then straight back up, and that's the second bang. And the shape of that N wave encodes information about things like the altitude of the source, the speed of the source, the size of the source, the aspect ratio, etc., etc. From the sort of ensemble of sonic booms that you might record at tens, hundreds of stations even sometimes, from that we can derive a trajectory, we can derive a speed, we can derive a descent angle, so we can tell how steeply this thing is coming into the atmosphere, but all of those things require us to have more than one station recording the sonic boom.
Applying all that to the California fireball, Ben and his colleagues were able to match the data up with a part of China's Shenzhou 15 spacecraft that had been left behind in orbit as the crew returned from the Chinese Tiangong space station in 2023.
We knew that this object, it would re-enter the Earth's atmosphere at some point. What wasn't clear was on which orbit, and therefore at what time and in what place this thing would re-enter. So the morning of April 2nd, 2024, there was a prediction that this thing would re-enter over the North Atlantic at about 8 o'clock in the morning, UTC, so 8 o'clock Universal Time. About the same time, but nearly 10,000 kilometers away in California, people start reporting an object burning in the sky. And it turns out that the trajectory that actually matches the spacecraft, Shenzhou 15, and what had happened is that it had re-entered the atmosphere quite a bit earlier than was expected. That's not unusual. And it was burning up by the time it crossed the coast of California, and it's these fragments falling off the spacecraft, putting on this light show over Santa Barbara, LA, Bakersfield, all the way out to Las Vegas. And so what I thought is, well, this is an area of the world which has an enormous number of seismometers, probably the densest or second densest seismic network in the world. What about if we look to see whether the sonic booms from this object have been recorded? A missile and a piece of space debris travel very different speeds. Similarly, a natural object is much, much faster than a piece of space debris, so can we try and figure out what this is from the seismic data? Lo and behold, we see this beautiful sonic boom signal propagating out all the way across the Southern California seismic network. And it's a path that almost matches what was expected for Shenzhou 15, but is a little bit further south of it as well. And that really highlights the reason that we need to track these things once they're in the atmosphere. Because if you're worried about this stuff falling on your house or your friend's house or something, 30 or 40 kilometers makes a huge difference to where toxic byproducts, etc., might hit the ground.
Well, this was an unusual event. It's likely to become increasingly common in the near future as Earth's orbit gets more and more crowded. Even satellites eventually obey the adage that what goes up must come down.
The number of objects re-entering the atmosphere is increasing at a basically exponential rate at this point. And a large part of that is to do with the SpaceX Starlink satellites. They make up a huge fraction of the re-entries in this day and age, but they're not the only culprits. And some of these objects are controlled deorbits, so we know where they're going to fall. They're designed to fall out over the open Pacific, which isn't great, but it's better than having them re-enter over Los Angeles. A large portion of them are just left in orbit, and no one really knows where they're going to fall out of the sky. And, thankfully we've actually been quite lucky so far. That's clearly not going to stay that way, because not only are there more and more people and more things to hit on the ground, the amount of stuff in orbit and the frequency, the mass of re-entries goes up and up and up over time. And so we have this problem, in space situational awareness, where we really don't know exactly when stuff is going to enter the atmosphere. And that's kind of an almost unsolvable problem. The other side of the problem is that once it does start re-entering the atmosphere, we have trouble tracking it. We have trouble tracking it quickly. We have trouble tracking it with anything close to the degree of precision or accuracy that we want using data that's open source / not classified. And all of those problems are things where I think seismic data can potentially be a help.
Now, unfortunately, this kind of system isn't going to be able to warn people ahead of time to take cover, but it could help us identify these events and find anything that survived re-entry and hit the ground.
So there's a very famous example in 1978. There was a Soviet spacecraft called Cosmos 954. It scattered radioactive debris all over northern Canada. And it took a while to find it. And there you have this concern where not only is there radioactive debris on the ground, the longer that it's on the ground, the more likely it is that it's incorporated into the ecosystem, the more likely it is that people come into contact with it and even if it's not radioactive, there are adverse consequences from some of the chemicals that we have on these spacecraft. So what I think we can do is not so much warning, but rapid response.
That would be a pretty important emergency management tool, but as is usually the case in science, this research began with basic curiosity about something completely different.
What I was initially interested in was looking at how waves propagate through the sun. And that's a really tough problem. It's very difficult to model. And so I started looking at modeling waves propagating in the ocean. And we realized that there was a lot of work that could be done but hadn't been done. And to go from the ocean to the atmosphere is actually really not that big a leap. So if you think about the physics of waves propagating in fluids, the ocean and the solid ground are actually very different. The ocean and the atmosphere are actually not that different at all. So I realized that some of the techniques that we were using to model waves propagating in the ocean on Earth could be used to model waves propagating in the atmosphere on Mars. And that kind of brought about looking at wave propagation on Mars. And of course on Mars, the sources, or a substantial set of sources, are those explosions in the atmosphere and sonic booms from objects re-entering. So we have this new set of techniques and expertise that we developed for use on Mars, which are just kind of sitting around now, and part of the realization that I and others have had is that there's plenty that we can apply them to on Earth.
The way you get from using a seismometer on Mars to tackling a new problem on Earth is that the physics are the same. So learning something in one situation can give you information about another very different situation. It's also really common that when we put in the work to collect data for one reason, other curious researchers dig around in there and find unexpected bonus science. I mean, generally speaking, we build seismic networks on Earth to measure natural hazards beneath our feet. But here it looks like they're also proving to be useful for human-caused hazards above our heads.